Hey, welcome back. In this lecture, we're going to be concluding the extendable hashing discussion. We left off last time looking at a table, and this is slightly different than the table that we talked about last time. And that, well, first, the keys are different. I've picked different keys. And secondly, we've got this little box in the corner there that we didn't have at the end of the last picture. Remember, I had told you at the end of the last lecture that the picture wasn't complete yet. Now it's complete, but we haven't talked about everything yet. Before I describe the rest of the table, let's go back and pick up that question I left you with. I had said that if we're going to deal with something such as looking for the value 100100, well, the prefix, the 3-bit prefix of 100100 is 100. And so we look up in the cell 100, follow the pointer, and search that cell. And I said, okay, what if these leaf pages happen to be pretty large? What if I had 200 values here, and now I'm looking for the string of all zeros? And it turns out now that I say, well, looking for the string of all zeros, the 3-bit prefix there is 0, 00. So I go to that cell, follow that pointer, and grab that leaf page. So we know if the string of all zeros is anywhere in the table, it's going to be in this top leaf page. And we search that top leaf page. And the question is, well, that's going to take a while. So why would this be of value to us? And we can perhaps make the table larger and have more nodes, but ultimately all we're doing is dividing our leaf pages into nodes. Dividing our keys into the leaf pages or into the nodes. And so whether we're dividing them across 4 nodes or 8 nodes or 16 nodes seems like it's not going to be a terribly useful thing unless we sort of grow the table dependent on the data size in some way. But we still end up having to search this leaf page. And the strength of extendable hashing comes from the same thing that B-trees had a strength for. The idea here is, if you'll notice, going from the table to the leaf page is going to be very, very, very quick. Constant time, in fact. It's even faster than the B-tree in that regard. If you have a table, you follow the pointer, you grab the leaf page. So if it happens to take us a while to search the leaf page, well, what would happen if the table had been in memory and the leaf page had been on a disk? In that case, it would have taken us, as we talked about in the B-tree lectures, quite some amount of time to grab the leaf page. And that being the case, since it had taken us some time to grab that leaf page, searching it would not have been a huge drag on the time, because it would have taken us some time to grab that anyway. Remember, we said the disk access was pretty expensive. So the time to read in that node from disk to memory would be comparable to the time that it takes to search the node. And so as a result, we don't really need to worry about the search time so much. Yes, there's search time. And if we're going to sort of calculate the cost of everything, if it was all in main memory, you'd say, well, 1 pointer access to go from table to node, and then you search the node for however long that takes. But it's got special appeal as a disk structure because we can say 1 pointer access from the table in memory to the leaf page on a disk. And so the idea there would be even better than B-trees as far as the speed issue goes. We'll talk about more of comparison of them later on. But we have the idea here of saying, I can go from memory to the exact leaf page I need to search in only 1 pointer access. Where for a B-tree, we would search down the tree, we'd grab a node, and that would lead us to a new node, and that would lead us to a new node, and eventually to the leaf. Here we're saying, if I grab that node, what I'm looking for is in that node, or it's not anywhere. So in constant time, I can get the leaf page I need. Then, searching the leaf page could take some time, depending on how you arrange things. If you keep them in a sorted array, maybe you use binary search, or you organize them as an AVL tree within a node, or an unsorted array, perhaps. But however you do things, you can speed up or slow down the search of the leaf page, but it's still you do have some expense you're comparing to already simply by the fact that you had to read it from disk. So there was a pretty large expense up front. If it takes a little while to search the leaf page, it's not too much of a drag on the time after what you've had to do already. So extendable hashing will be most strongly used in disk access structures, just like B-trees were. And so if you should happen to take 311 at some point, the database course, you'll see both B trees and extendable hashing, as I think I maybe even mentioned that in the B tree lectures. You'll see B trees and extendable hashing in that course. More variants on them and such than we're going to go over here. But both B trees and extendable hashing are used extensively for databases and other such disk access-based tools. So that's the idea there. Now, as far as we've now talked about how to actually do a lookup in this table. You pick out the appropriate prefix, look up that prefix, jump to that node, and then search the node for what you want. And that helps you find your key. Now, what we have to do is talk about insert. But in order for insert to make complete sense, what we need to do is talk about the last thing we haven't talked about yet, which is this little square in the corner with the appropriate, with a number in there. This is known as the leaf page depth. So what we say here is we've got this set up, and we say here I've got forget that. Let me draw it here. When we have a node, the number here, whatever it happens to be, is the leaf page depth. So the idea here now, what is that leaf page depth? Well, the leaf page depth is going to be a measure of how many bits matter in this particular node. What number of bits divide the stuff in this node from the stuff in all the other nodes we might have? So for example, coming back to here, we say, notice that because of the fact that all the 4 3-bit prefixes that start with 0, there's 4 of them, all of them point to this node. That means that if you start with 0, if your bit string starts with 0, it's guaranteed to end up in that node and nowhere else. All the other nodes deal with prefixes that start with 1. So, therefore, you only need to look at 1 bit of a bit string to determine that it goes here and nowhere else. That is, a 1-bit prefix defines this node. It is the 0 node. Likewise, down here, we can't say it's the 1 node because there are 3 different nodes whose appropriate prefixes start with 1. So you can't say any of the nodes is the 1 node. However, you can say down here, this is the 1-1 node, which is why we have a 2 there for the leaf page depth. We say if you were to look at 2 bits, that's enough to determine whether a value goes into this node or not. If it matches in the 1-1, it goes here. If it's 0-0 or 0-1 or 1-0, it goes somewhere else. So looking at 2 bits is enough to determine that a key either goes in this node or that the key does not go in this node. 1 bit was enough here. As soon as you see a 1 for your first bit, you know it doesn't go there. As soon as you see a 0, you know it does, regardless of what the rest of the key is. 2 bits is enough here. Regardless of what that 3rd bit is, if it starts with 1-1, it's going to go here. If it starts with anything else other than 1-1 in the first 2 bits, it goes somewhere else. And likewise, this is 3 because we say, well, we're looking at 3 bits, and we need all 3 to determine it goes here. There's no 1-0 node because we have 2 different nodes that contain prefixes that start with 1-0 or contain bit strings that start with 1-0. And so we need to look at the 3rd bit and say if it's 1-0-0, it goes here. If it's 1-0-1, it goes here in the 3rd node. So that's the leaf page depth. It, in a sense, indicates how many bits define this node. We only need 1 bit to define this node. If it's 0, it goes there. If it's 1, it doesn't. We need 2 bits to define this node. We need to look at all 3 to define here. So there are some cases where you're looking at a particular prefix in the table, and maybe all the bits matter. In the case of your 2nd and 3rd nodes, 1-0-0 is used to determine it goes here. 1-0-1 is used to determine it goes in that 3rd node. There are other cases where even though you're looking at 3 bits, they don't all matter. And an example is these top 4 cells. I have 4 different indices there, 4 different 3-bit indices, but no matter which of those 4 prefixes I'm looking at, The only bit that's really important is the first one. I do have a second and third bit, but for the moment, the way this table is structured right now, the second and third bit of those 4 prefixes don't matter, because regardless of what the second and third bit are, it ends up in that leaf page. And likewise, for these 2 cells down here, there are 3 bits, but the third bit doesn't really matter, because regardless of what it is, you end up here. If you're looking for 100, you end up in this node. If you're looking for 111 or 110, you end up in this node. 111, you end up in this node. So the third bit didn't really make a difference. The first 2 bits alone determined you ended up here, and so we didn't really care what the third bit was. And that points out an important relationship between the number of pointers on a node and the directory and the leaf page depth. If you notice in this table, let me go ahead and put this here, there's going to be a relationship between D, which is the directory depth, and little d, which we'll use to notate a particular depth of the leaf page, and number of pointers to that leaf page. There will be a relationship between those 3 quantities, and we can look at that, figure that relationship out by looking at this table again. We can say, well, looking at this situation here, I notice I've got 4 pointers to that top node. The reason there are 4 pointers to that top node is because there's 4 different cells that had 3 bits. I'm sorry, 4 different cells that started with 0. All of these prefixes, these 4 prefixes, had 3 bits, because every index has 3 bits. So we have 0 through 3 there. The binary number is 0 through 3. And yet, because all that really mattered was the first bit, 0. This node contains everything that starts with 0. Because we looked at 3 bits, but we only needed 1, that's going to mean we have multiple pointers to this node. Here it's different. We're saying I have a 3-bit prefix, and that 3-bit prefix uniquely ends up here. Anything else that doesn't match this prefix in the slightest goes somewhere else. So we have exactly 1 cell that points to that node, and if your third bit is different, or if your second and third bits are different, you're going to point somewhere else. Where here, we're saying, yeah, 000 does point to there, but there are other nodes that point to here too. In other words, there's a difference between the directory depth and the leaf page depth, and that tells us there are bits left over. We're saying, since the bits that really matter are less than the number of bits we look at, well, if I only care about 1 bit, but I'm looking at 3, that means there's going to be 4 different values that start with that 1 bit. If I look at 1 bit, we're saying, well, anything that starts with 0 ends up here. If I'm looking at 3-bit prefixes, that will give me 4 values that start with 0. If the depth had been 4 and I had 4-bit prefixes, table size of 16, if I only needed the first bit, well, how many cells match in that first bit? 8 of them. The first 8 of the 16 4-bit numbers all start with 0. Just like the first 4 of the first 4 3-bit numbers start with 0. Likewise, the first 8 4-bit numbers would start with 0. And if we shrunk this to size 4, and we had 0, 0, and 0, 1, and 1, 0, and 1, 1, which wouldn't make this work anymore. But just think about this node. Then if we only care about 0, but there's 2 bits we're worrying about. The point being there's leftover bits. And that's what these combinations are. We have this idea here. If I'm pointing to, let me write this here. If I'm saying here I have anything that starts with 0 points to this node, which has the leaf page depth of 1. And we're saying, well, I'm being told to look at 3 bits. So I have here 4 possibilities for the leftover bits. They all start with 0. That's what matters. But the point is, since I only needed to look at 1 bit for real, or not for real, but since conceptually I only needed to look at 1 bit, but I was being told to look at 3, that means I will be ignoring 2 of those bits. We're saying only 1 of these bits conceptually matters in terms of landing you in this node. But in reality, you have to be looking at 3 of them. So 2 of them are not needed. And since we can ignore them, since they're not needed, since we end up in that particular leaf page regardless of what those 2 bits are, those 2 bits can be anything we like. In fact, they can be every possibility. And there's 4 possibilities for them, therefore 4 pointers. And that's exactly what's going on here. What we are saying is, since I only needed to know that you've got 0, that it starts with 0 to end it up here, that means that whatever bits 2 and 3 are, you end up in this node. And that means the particular value for bits 2 and 3 is irrelevant as far as what gets pointed to this node. So in other words, the 0, 0, 0, 1, 1, 0, and 1, 1, every combination of those second and third bits will point to this node. There's no distinguishing them. It's irrelevant. If you start with 0, you end up here. So since every string that starts with 0 ends up here, regardless of what the second and third bits are, it should follow that every prefix, no matter what it has in those second or third bits, should point to here as long as it starts with 0. And how many of those are there? Well, all the prefixes that start with 0, there's 4 of them. And so there's 4 pointers. Likewise, down here, I'm saying you start with 1, 1 to end up here. And so we're saying, well, how many prefixes do we have that start with 1, 1? We have 2 of them. Because we're looking at a depth 3 table, and so our concern is we have 2 prefixes start with 1, 1. The third bit doesn't matter. Regardless of what the third bit is, you end up here. And so both cells should point to that spot. The cells matching all the possible combinations of that third bit. When the third bit is 0, you point to this node. When it's 1, you point to that node. Therefore, you have a leaf page depth of 2. You have 2 pointers to this. That is, our formula is you take the depth of the table minus the depth of your particular leaf page. That tells you how many bits are left over that don't matter in terms of getting to this leaf page. And then how many combinations you have of those bits? Well, 2 to that quantity. Two to the table depth minus leaf page depth gives you the number of pointers to the leaf page. That's how many you're told to look at. That's how many you really need in this particular leaf page. The difference is sort of the wasted bits. How many combinations of wasted bits are there? 2 to that number. And every combination has its own pointer to that node. And so that leads you to then that table. When the leaf page depth is 1, 3 minus 1 is 2. 2 to the 2 is 4. We have 4 pointers. 3 minus 2 is 1. 2 to the 1 is 2. We have 2 pointers. 3 minus 3 is 0. 2 to the 0 is 1. We have 1 pointer. And that's the relationship that goes on here. The relationship between the leaf page depth and the table depth and the number of pointers. What we're saying here is, since everything that starts with 0 has to point to this node, that means the second and third bits, regardless of what those second and third bits are, you'll point to that node. And that's saying every combination of those second and third bits in a prefix results in a cell that points to that node. And since there's 4 combinations, there's 4 pointers. And so that's the idea there. That's the concept of the leaf page depth. What this does mean is that we cannot get tables that are broken up like this. And we're just sort of going to look at the top half of the table. You can't get a situation like this. If the depth is 3, where you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, where you have a situation. Certainly we could say, okay, we've got a 3 here. This is the 0, 1, 1 node. And you could put a 3 here and say this is the 0, 0, 0 node. But what do you do here? if you give this a leaf page depth of 1 and say it's the 0 node, that's not true, because there are other prefixes that also start with 0 that don't end up in that middle node. Yet, if you give it a leaf page depth of 2, what prefix would that be? We don't have a common prefix of size 2. This node, the stuff that would go in this node, the pointers that go to these nodes, have only a common prefix of 1. And you have to have a common prefix for a node. We have to say everything that starts with 0, 0 is here, or everything that starts with 1, 1 ends up here. So there's this concept of a common prefix. Everything that shares that prefix ends up in that node. And the issue here is, well, the only prefix these two cells share is 0. And so the only option we'd really have for a leaf page depth would be here, because they don't share a prefix of anything more than 1 bit. But other cells have that same 1-bit prefix. And if we're going to say everything that starts with 0 ends up here, well, that's not true if there's other things that start with 0 that end up elsewhere. So the structure you see on that page cannot exist. The leaf page contains not only, the leaf page contains, let me actually write this down. Leaf page depth indicates common substring length. All strings with that substring as a prefix and no others are in the leaf page. That's our rule, that the leaf page depth is going to indicate the length of the common substring of all the stuff that goes here, or all the stuff that could go here. And so as a result, all strings with that substring, all the strings with the, in this case, the reason this doesn't work is we're saying, well, if your common substring is of length 1, you don't have all substrings with that prefix, because there's some others. And also, no others have to go there. And so that's the idea here. Everything that starts with 0 ends up here, nothing else. Everything that starts with 1, 1 ends up here, nothing else. Everything that ends up with 1, 0, 0 ends up here, and nothing else. Everything that starts with 1, 0, 1 ends up here, and nothing else. And so because of that rule, we don't need to worry about arrangements like this. They can't happen. You can have these two pointing to one place because they share a further substring of 0, 0. And in fact, we're going to show that in a minute. But this idea of kind of dividing it up like this won't work. You have to have a common substring of the cells that point to your node have to share a common substring. And the longest common substring they share, you have to then, inside this node, contain everything that shares that substring, not like we have here, where you have other nodes that share that substring, that are other keys that share that substring that are somewhere else. So then, at this point now, everything in this table we've explained, and that's how this all works. And so the issue now is to deal with insert, which is the last thing we're going to talk about. We'll mention at the end kind of what's sort of goofy about remove. Not goofy, but I should say we're not really going to talk about remove. Just look up and insert and understanding what the table structure is. And so the last thing we need to worry about is insert. So to insert some sort of a key, you hash on key to get your bit string, and you get the D bit prefix of the bit string. Find that prefix in table. In other words, i.e., what table index, what directory index is that prefix. If your prefix is 110, then that means 6. So those are the first 3 steps. You hash in the bit string, you get the d-bit prefix of the bit string, find that prefix in the table, go to the leaf page that table cell points to. So far, so good. This is exactly what we've done with find. These are the first 4 instructions for find as well. Hash your key onto your bit string, get the capital D, the directory depth, bit prefix of the bit string. You find that prefix in the table, go to the leaf page that table cell points to. Now we're at a leaf page node. That's exactly what we did for find. At this point, find would have said, search that leaf page you're in. Insert instead says, insert bit string into leaf page. Not done yet, but that's the start of this. Now, in reality, you may be inserting the bit string into the leaf page. You would probably have your key or your record or something there as well, or point into that record. So, I mean, you have the other information added as well, but we're just talking about the basic idea, and I know you can kind of extrapolate and say, okay, we have this and a pointer to some record or something like that. We're just concerned about how to actually get the keys where they're supposed to be. Any data that comes along with the key is, of course, going to go to there as well. So that's 5th step, the only step that's different so far. Instead of searching for the key, we're not trying to find it, we're trying to insert it. So you insert the key into the leaf page. And so we have 3 options now. So that's the easy part, to actually get to the leaf page and dump a value in there. When we talked about this being ideally set up for a B tree or for a disk-like structure, we had also said, well, we need to have a bound on these nodes. If I start out with 4 leaf pages in this table and I just start dumping keys into them indiscriminately, eventually I end up with just huge amounts of data in a given leaf page. So unless we want to restrict the time it takes to search one of these nodes, we have to bound it, as we said before. And because of the way that it's based on a sort of a disk structure, or can be used for disk structure, typically the bound on the leaf page is going to be one that is dependent on the disk block size. So we say whatever the maximum extendable hash leaf page node would be, that should fit as snugly on a disk block as possible. We're to the point where if you were to make it one larger in an upper bound of size, then that particular leaf page would not fit on one disk block anymore. So you want your size to be set up so that this just fits on a disk block in its maximum size. Just like the B tree node, we said when it's got the most number of children possible, and therefore, number of indices was 1 less, we said that kind of a node should just barely fit on a disk block. As large as possible, so that if we made it a little larger, it would run off, it would be larger than a disk block. As large as possible and no larger, and that's how this works as well. So, as a result, the leaf page size is bounded. Say B, we can use B for the size. That's what the book does as well. It just uses a little b and says wherever your size is b, and then here's your blah, blah, blah results. We will use b equals 2. I think there are also some other examples where we say b equals 4 on the past exams and such. Anything from 2, 3, 4, 5, very low numbers, very low bounds are fair game. I mean, you should understand how to do this no matter what the bound is, but I'm telling you, we're not going to give you a leaf page bound of 200 on an exam, because you'd be rewriting or drawing or rewriting nodes for 200 keys. If you can deal with this on nodes of size 2 or 3 or 4, then certainly you can deal with the same issues on a size of 100 or 200. It's just a matter of we're not going to have you copying endlessly bit strings on an exam. That's kind of a colossal waste of time. So instead, we're just saying, okay, we'll use small bounds, small b values for an example, just like we did for B trees, where we said normally you'll have a much higher order B tree, but we'll have an order of the tree B3. The bound of our disk block here, the bound of our leaf page, we'll say is 2, or you might get 3 or 4. We'll always tell you in a given problem. But in reality, you'd have something like 100 or 200 for your leaf page size, so that would fit on a disk block. So there are 3 possibilities here after you do this insertion. No overflow. 2 is going to be overflow, and 3 will be an overflow case. So we'll deal with 2 and 3 in just a moment. But those will be our 3 possibilities. It'll be like the B tree remove, where there were 2 different kinds of underflow cases. Likewise here, there's 2 different kinds of overflow cases. But the first case is no overflow. So we have the idea here of our insert algorithm. We say hash on the key to get the bit string, look at the prefix of that bit string, use that as an index into the table, grab the leaf page that table cell points to, and then insert your key, your bit string, into that leaf page. And once you do that, then either you won't overflow or you'll hit one of the 2 overflow cases that we had. So our example here is going to be inserting 100,001 into the original table. The second example we're going to deal with here is going to be inserting 010010 into the original table. And our third example here that we'll deal with, we'll come back to this slide, so if you don't want to write these bit strings down quite yet, everything will be cool. We're going to deal here with 101111. And so those will be the 3 values we'll insert. So let's go ahead and look at the first table. We're going to insert 100001. Oh, let me put that back, actually. So the first one was hash the key to the bit string. So whatever our key was, it would have hashed to that bit string. We're sort of skipping over that first step. We take some sort of key, some name, string, whatever, hash it to that bit string. And now we have 100001. Now we get the 3-bit prefix of that string, because our table depth was 3. The 3-bit prefix is 100. Find 100 in the table, follow that pointer to the leaf page node, and then insert the string 100001 right inside this node. And so that Charles can scan in stuff one by one, and you can sort of, that makes his life easier. I just made a different slide instead of writing it in as we talk. So it's actually a different color too, but it's not showing up too well on the screen. You might vaguely see that that's black where everything else is red. But anyway, I can actually at least draw an arrow, I should say. There's the new value. Instead of writing it on the old slide, I just have a new redrawn slide with that value there. So that takes care of that issue for us. We've got now that string's been inserted. And if our bound was 2, if we could have at most 2 bit strings in any one node, well, that doesn't violate anything. We've got 2 bit strings now. So there's no problem there. Everything's cool. Nothing's violated. So we can stop. And that's the answer here. All you do is stop. If there's no overflow, you're done. You were able to insert into that node without a problem. The second case is when we overflow and the node will be too big. So here we're going to say I'm inserting 010. So I would have hashed on the key to get that bit string. The prefix of that, the 3-bit prefix, is 010. We find 010 in the table. We follow the pointer into that node, and we go ahead and insert the value into that node. So that would look like this then. There's the new value. We had 0, 0, 0, 0, 0, 0, and 0, 1, 1, 0, 1, 1. Now we add a third example, a third bit string, 0, 1, 0, 0, 1, 0 into there. And the problem is, if we're only allowed to have two bit strings per node, well, now we've got three. We've got a problem. How do we fix that? And the answer is going to be similar to the B-tree node, where when it got too big, we split it in half. We're going to sort of, in a way, split it in half as well here. I'm going to redraw that one node on a separate piece of paper. So we've got here 1, and we have here 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, and 0, 1, 0, 0, 1, 0. No reason the first three bits have to be the same as the last. That just happens to be some of the strings I made up. So it seems as if there's duplicating pattern here for some of these. Anyway, the idea here now is we've been looking at the first bit all along. This was the 0 node, because all these nodes share the common substring of 0, and no other node anywhere in the table has a common substring of 0 for the first bit. Now, however, since things are too big, looking at one bit alone isn't enough. We've been saying anything that starts with 0 all gets packed into one node, but now there's too many of those things that start just with 0. So what we want to do is say we need to look at a second bit now. That is, we need to create, instead of having everything that starts with 0 packed into one node, we'll have a 0, 1 node and a 1, 1 node. And this is why it was important for the keys to be evenly distributed over 0, 1 and 1, 1. However many keys we have that hash to 0, that start with 0, we're then saying out of all of them, we want half of them, half of those keys, the ones that start with 0, half of them should go to 0, 1, half of them should go to 1, 1. That way, what we expect is a large number of keys, however many there are here, we expect half of them will end up in that node and half of them will end up here. Where if instead, everything that hashed to 0 hashed to 0, 1 as well, and nothing, anything that started with 0 started with 0, 1, and there were no 1, 1 keys, we'd have, 100 or 200 things that start with 0 here. They'd all end up in this node, and none of them would end up here. Or a large number would end up here, and only a few here. And that's not going to do us much good. What we want is an even distribution. We'd like this node to split roughly in half. And so if the hash function is working correctly, and we do indeed have a hash function that says everything that starts with this particular 1-bit value hashes evenly to the second bit. Half have one possibility for the second bit, half have the other possibility for the second bit. Then we'll roughly split this in half. Now the question is, what happens when that's not the case, when by some weird freak of nature we have 200 values that not only start with 0, but all start with 0, 0 as well, and we'll talk about that at the end of this lecture. But in almost all cases, it's very unlikely we would get anything other than a nice even split or approximately that. We really don't expect, certainly, I shouldn't say we may get some more nodes here than here, depending on how things have distributed. I should say what is extremely unlikely is that we'd have everything hashed to 0, 1 and nothing show up at 1, 1. That if I look over these bit strings, they all start with 0, 0. Because when in reality we have like 100 or 200 of them, it's extremely unlikely all of them would start with 0, 0 I'm sorry. What the heck did I write here? I'm very sorry. That should have been 0, 0 and 0, 1. I think I've been saying 0, 0 and 0, 1 and didn't write the right stuff up there. I'm very sorry. Hopefully you knew what I was talking about. So the idea here is we would hope, so hopefully my earlier explanation was followable then, that everything that starts with 0, 0, everything that starts with 0 could have 0 or 1 for the second bit, and we see those possibilities here. 0 or 1 for the second bit. And we hope that about half of them have 0 for the second bit and about half of them have 1 for the second bit. We expect it's very, very, very unlikely, if our hash function is good, that we happen to have, by some coincidence, picked 200 values that not only start with 0, but also end up there. Because certainly we have a huge number of different keys and the possible bit strings from them, and our hash function may well say, well, certain values will start with 0, 0, and certain ones will start with 1, 1. And it's possible that by coincidence, we've happened to have chosen things that happen to all hash to bit strings that start with 0, 0. It's possible, but we don't expect it's likely. We expect that given, however many random keys that hash to our various bit strings, we expect we're selecting keys that some of them will hash to 0, 0 and some of them will hash to 0, 1. Just like we said, it's possible if I pick 7 integers at random, they're all going to be integers that hash to 2 if my hash function is, x mod 7. I can pick 7 integers at random. They might all be equivalent to 2 modulo 7. But probably they're not. Probably I get a better distribution than that. And the same thing here. I may pick 200 keys that all happen to hash to a string that starts with 0, 0, but probably given 200 keys that start with 0, half of them will have 0 in the second bit and half of them will have 1 in the second bit. Or, maybe it's slightly off proportions from that. Not everything in one node, everything in the other. So hopefully now that I've explained at that time with the right numbers on the page, then it makes more sense. Sorry about that. So the point being here then that each of these now has a leaf page depth of 2 because we need 2 bits to determine it goes here. It's not enough just to say, hey, 0 is all that matters, because 0 isn't all that matters anymore. We'll have 2 different nodes containing keys that start with 0. But if we look at 2 bits and say, well, the 0, 0 things go here, then that's true, because we say none of the other nodes had anything that starts with 0. And this is the only other node that had anything that starts with 0, but they all start with 0, 1. I'll write this here. And I'll say these go here. And essentially this splits into those 2 nodes. So we're saying this, we know that applies because there were no other nodes in the table that anything started with 0 to begin with. All the other nodes, things started with 1. Now we're saying everything else in the table still starts with 1, except for this other node, my co-partner in the split. But that starts with 0, 1, and I start with 0, 0. So if I say everything here starts with 0, 0, I know that's a unique safe statement to make. That everything here starts with 0, 0, and nothing anywhere else starts with 0, 0. All the nodes that start with 0, 0 end up here. Because the stuff that was here were the 0, 1 nodes, and nothing else in the table even started with 0, let alone 0 with a second bit of some kind. In other words, the second overflow case, it's handled by saying what we will do here is say we split the node. And indeed, in general, that's going to be the case. So even this third overflow case, when we look at in a moment, we will split the node. Now the question is, what happens here? If I look back on that table, I took this node and I split it. So we've seen how it splits now. Let me replace this picture with the newest picture, which is this one. The only difference there is now I've drawn the node, the split, and I took care of that. This was what we showed, how the original node split into 2 new nodes. And then here's the result inside the table. And what we see has happened here is that we had enough pointers to go around. In the original table, I had 4 pointers pointing to this node. So I can put 2 pointers on each. I had all the 0 pointers pointing to the 0 node. Now I have these 0, 0 pointers pointing to the 0, 0 node, and the 0, 1 pointers pointing to the 0, 1 node. And I'm saying now, just like down here, it's the third bit that doesn't matter. The second bit now matters. We used to have 4 pointers that all start with 0, pointing to, or the whose indices all start with 0, pointing to 1 node. Now that the second bit matters, and we've split this node into 2, now we're saying things that point to here are the 0, 0 element, 0, 0, 1 or 0, 0, 0. And so those are those 2 keys. And likewise, we're saying, since everything that starts with 0, 1 is now going into here. Any index that starts with 0, 1 should point there. And there, therefore, is a third bit wasted, and that third bit can be either 0 or 1, and it'll still point to there. But what we've done is we've said, since that second bit now matters, depending on the original value of that second bit, when we had all 4 pointers pointing to one node, we say, well, out of those prefixes, the one with a 0 in the second bit point to one of the new nodes, and the 2 with a 1 in the second bit point to the other of the 2 nodes. Now that second bit is significant, and we deal with it. The third bit still doesn't matter, so we don't care what the third bit is. That can be 0 or 1 in either case. And so that's how that's taken care of. The reason we were able to do this is because we had extra pointers. Or in other words, resultant depth of the 2 new leaf pages is less than or equal to the table depth. We have enough pointers because the depth of the leaf page is not greater than the table depth. If the depth of the leaf page has been greater than the table depth, we wouldn't have enough pointers to go around. And we'll see an example in a second. That'll be exactly the case 3 issue. Here, the resultant depth of the 2 new leaf pages will be greater than D, where here we're saying we do the same thing at first for both of them. We insert some key, and we therefore split the, we have things. Let me actually, maybe I can draw lines through here to make that a little easier to read. I don't know if that makes things easier, but hopefully it does. So we started out the 2 overflow cases the same way. This overflow case, we said the resultant depth of the leaf pages is less than or equal to D. Here, it's going to be greater than D. And so when it's greater than D, the action we'll have to take is to split the table. Or in other words, if the table does not have enough pointers, what we're going to do here, and I'll write it out once we get to that point, we're going to have to split the table as well, increase the table, make the table larger so to provide us with more pointers, and then we'll have enough pointers for the nodes. But anyway, we'll talk about that in the next example. This is how we've handled things. The result, we split the node, resultant depth of the 2 new leaf pages is less than or equal to D, so we assign pointers and stop. And I'm not sure if it's terribly readable, but anyway, that's how that happens there. When the resultant depth of the 2 new leaf pages is less than or equal to D, we will have enough pointers. So you just assign the pointers and you stop. And that's exactly what we did here. We had 4 pointers for 2 nodes. We assigned the pointers appropriately, 2 pointers per node, and we stopped. And the 2 pointers had to be in sequence. So I didn't say these 2 pointers point to one and these 2 point to the other. In other words, 0, 0, 0 and 0, 1, 0 didn't point to one place. And then the 0, 1, 0, 0, 1, and we didn't do something like this, where these 2 pointers go to one node and these go to the other, because then there's no common prefixes, like we talked about before. We say these 2 have a common prefix of size 2, these 2 have a common prefix of size 2, so that's okay. So that kind of assignment is all right, because there's a common prefix here and a common prefix here. If I'd done something like this, where these were to one node and these were to another node, that would not work. That would then, we wouldn't have the common prefix and the whole structure would be messed up. And so we've said, okay, the first 2 that have a 0, 0 prefix go to one place. The second 2 that have a 0, 1 prefix go somewhere else. That said, now let's look at the third case. Our third example, we said we have 0 or 101, 111. So again, that we hashed some key to get to that bit string, check the prefix, it's 101, go to our table and say 101 is here, follow the pointer in that leaf page, dump the key in that leaf page. And so here's the new picture, and this is what we just did before, and now there is the new node. We had 101, 110, and 101, 001 in that node. And now, in addition, we've added below them 101, 111, which is what we wanted to insert here. And so we can go through and split that again, and we talked about how to do that. We would say, well, right now, this is the, I'm going to go ahead and redraw this here. We say this is the 101 node, as we can see by only one pointer pointing to it. And we had a depth of 3 here, and this contained, I'm going to run out of room here. This contained 101, 1, 1. Let me start again. That'll work better. So here's the 101 node, and this contains 101.100, 101.001, and 101.111. These 3 have been copied there. And probably this is the only slide you're seeing, but I'm keeping the table here so you can kind of see that on the video at least. And now we say, well, they've been the same in the first 3 bits. Let's look at the 4th bit now. And we'll say, we'll split this into, this value has a 1 for the 4th bit, this value has a 1 for the 4th bit, this one has a 0 for the 4th bit, and so that's how we'll split those. We say here we have leave page depth of 4 with 101, 001, and here we have a leave page depth of 4, and here we have 101100 and then 101111. So this is now the 1010 node, and this is the 1011 node. 101, but now the 4th bit matters, and so the 4th bit being a 0 or a 1 depends on which node it goes into. And so that split being done, we can now say, well, I'm going to take these 2 nodes and replace this with those 2 in the next picture, and so we've got that picture. Which is, I'm just replacing that node that was here with the 2 new nodes I drew on the last slide. And as we can see, this worked just like last time, except that we don't have enough pointers. We only had 1 pointer to the original node. And so now that we have 2 nodes, we're out of luck. The reason being that the increasing of the leaf page depth from 3 to 4 now means the depth of a leaf page is deeper than the table. And that was our condition here. Case 3 is when the resultant depth of the leaf pages is greater than the table depth. And I was saying split table before. That doesn't really make sense. We want to increase the table size. Most commonly, it's going to be a double. But we increase the table size, and I'll talk about that at the very end of the lecture. Most commonly, you can actually kind of extend this a little bit, but this is the basic idea. Increase table size. I'll write a double in parentheses. And there's sort of a slight tweak exception to 2 or 3, but it'll be the thing that really doesn't occur too often. I'll just go over it, but the basic rules will be just like what I write here. And the ones you need to worry about are what shows up here. Split the node into 2 nodes, the table size will double. That is, what I need here is to say, I need to increase the table size so that I have 2 pointers here instead of 1. That is, here's my table right now. This is the 000 cell, 001, 010, 011, 100, 11, 101, 110, 111. Those are my 8 cells. What I'm going to do now is say, let's imagine dividing each of these into 2 parts. That is, we're going to add a 4th bit, and that 4th bit can be 0 or 1. Meaning we have here 0, 0, 0, 0, 0, 0, 0, 1. And wherever this was pointing, wherever this table cell originally had been pointing, we should have both of these new cells point to that same place. Likewise, we have here 0, 0, 1, 0, 0, 0, 1, with the new fourth bit as 1. And similarly, wherever 0, 0, 1 was pointing, we're now saying, well, anything that started with 0, 0, 1 goes here. Well, likewise, anything that starts with 0, 0, 1 goes to that same place, whether it happens to be 0 or 1. Since we haven't changed the rest of the nodes, we don't need to change where everything points to. We originally said anything that starts with 0, 0, 0 follows this pointer. So now if we're looking at a fourth bit of the prefix and we're saying anything that starts with 0, 0, 0 originally went into whatever this node was, now we're saying, well, whether that fourth bit was a 0 or 1, it would have gone in this node. So this pointed to some node of some kind. Well, there's no reason those should change. If starting with 0, 0, 0 meant it ended up here, and what that means was we didn't care about a fourth bit. Whether it was a fourth bit or 0 or 1, we originally weren't even looking at a fourth bit. We simply said if it's got the 3-bit prefix of all zeros, it ends up here. So now if we're looking at a fourth bit, we're saying, okay, now there's two different categories there. There's things that started with 0, 0, 0 and had 0 as a fourth bit, and there's things that started with 0, 0, 0 and had 1 as a fourth bit. However, since we weren't even looking at a fourth bit before, the 3-bit prefix made it end up here. So now if that fourth bit happens to be a 0 or it happens to be a 1, it's still, either way, it would have been in that node. We may later split based on the fourth bit, but we haven't done so yet. So everything that was in this node when it was just a 0, 0, 0, now that we're looking at a fourth bit, we haven't changed what was in this node or rearranged this node in any way. Now that we're looking at a fourth bit, if it had 0, 0, 0 for the first 3 bits, it's going to be here whether its fourth bit is 0 or 1, because we didn't even care about that fourth bit before. So anything that started with 0, 0, 0 went there. Those two are both things that start with 0, 0, 0. They'll both go there. Later on, we might split it, though. And the same thing likewise here. You'll have had each of these table cells will have pointed to something, giving you 8 pointers in all. Some of them may have pointed to the same nodes. Likewise here, if anything that pointed to 1, 1, 1 ended up in whatever node this would have been, likewise, that means now if it was a fourth bit of 0 or a fourth bit of 1, we didn't even care about that fourth bit. So either way, it would have been in here. And so those 2 pointers should continue to say, well, look in that node. Because I know if it started with 1, 1, 1, it would have been here. Now that I know in more detail it's 1, 1, 1, 0, it ends up here. And likewise, if it started with 1, 1, 1, it would have been here. Now that I know with more detail it's 1, 1, 1, 1, I still know it ends up here. That may change later, but at this exact moment of splitting the table, that's how it works. And that'll be all the way down on the line. What we're basically saying is a new table of I, or I should say, the new table of 2I equals the new table of 2I plus 1 equals the old table of I. For I equals 0 to 2 to the old d minus 1. So the old d, I'm sorry, minus 1 is on this level. The old d was 3, 2 to the old d is 8, 8 minus 1 is 7. So what we're saying here is for I equals 1 to 7, for I equals the 2 to the old depth minus 1, or for I equals 0 to the old size minus 1. Traverse down every cell here from 0 to 7 and say, whatever that index is, 2 times that and 2 times that plus 1 will be the new indices. So whatever 0 pointed to, 0 and 1 in the new table point there. Whatever 1 pointed to, 2 and 3 in the new table point there. Whatever 2 pointed to in the old table, 4 and 5 point there. Whatever 7 pointed to in the old table, 14 and 15 point there. All the way down the line with that picture. And so when we split this, when we take this table and double it, 101, whatever 101 pointed to 1010 and 1011 will now point to that. And so these are those two pointers, 1010 and 1011. Those are the two pointers that point to wherever the original pointer pointed to. And now we have those two pointers to divide up among the two new nodes. And that's all there is to say here. The only other worry is the issue of saying, well, what happens if they had all gone into one place? And I said here, if I had, if I had done something like this, and all the stuff I had here, if I split this to 4 and split this to 4, and they all ended up here, well, then I need to split it again. Look at the 5th bit. So this would stay empty, and then I say, well, now that goes to 5, and maybe half of them go there, and half of them go there. We wouldn't have you do that on the exam, but that was to be the situation. If you had a bad hash function or a really small bound to your node size like we do here, you could end up with everything in one node and nothing in the other node. In that case, then you'd say, I split that node again while leaving that empty, and you get 5, 5, and 4 as a result. And so if your table size had been, table depth had been 3, and you have to increase your deepest node to 5, you may have had to quadruple the table size. Those are the odd things that can happen if you have a bad hash function or a very, very small depth. But don't worry about that because it's not likely to happen. That's it. That's the end of hashing. We'll do priority queues next time. See you then.